All right, so we've seen now what these problems are about, and now let's quickly focus in a little bit on this plane stress problem. Let's zoom into this one and see what we learn from this. Okay, when we look at a little bit more at the detail. So essentially this plane, let me just make it so that I can see. So in this plane stress problem, essentially, we've learned now if you pull on this in all the loading and all the boundary conditions and symmetries of the material is such that the response will be planar, we essentially know that these following terms, the sigma zz, the no out of plane stress, and all the shear components will be 0. So what do we learn if we know that these components will be 0? So let's look at the details again. Let's go and look a little bit at the detail. Okay, so let's look at our full three-dimensional constitutive relation matrix, and let's see what the implication is. So first off, let me just find my component. This is the component that will be 0. Okay, so this component will be 0. So this whole equation that I've got here, I can now multiply it out and say that it's going to be equal to something that will be 0. So I can say this Poisson that I've got here will multiply with epsilon xx. The next Poisson that I've got will multiply with epsilon yy. And then I've got the 1 minus Poisson that I've got. This will multiply with epsilon zz. Okay, so that is what I have. And this will be equal to 0, because this is what we have. If I sum it all together, it will be equal to 0. And what I learned from this is that epsilon zz is essentially equal to, take this to the other side, negative Poisson divided by 1 minus Poisson times epsilon xx plus epsilon yy. And I can write it out like this if I want. 1 epsilon xx and negative Poisson 1 minus Poisson epsilon yy. The reason I just write it out like this is because what I would like to maybe do is to say, if we have this expression and we already can solve for epsilon zz from epsilon xx and epsilon yy, then I can actually go and say, let's delete this whole, let's remove this whole expression, this whole equation. Let's remove this whole equation. I can't just delete it. And for this expression that I have here for epsilon zz, okay, I can now substitute and say what should stand there actually is minus Poisson 1 minus Poisson epsilon xx and minus Poisson 1 minus Poisson epsilon yy. And if I look at what this multiplies with, this whole column here, I would like to maybe try and remove this column as well. So this is the column that we would have multiplied with epsilon zz, and I see essentially this one and this one multiply with the same thing, so multiply with a Poisson. So essentially I can say, if we take a Poisson squared and a Poisson squared, I multiply the Poissons with these terms, then I can bulk these terms here, the epsilon xx term, I can then say it just needs to be summed here. So it needs to be added there, and this term here that I've got for epsilon yy, it needs to be summed here with the epsilon yy kind of place where it would have gone in. And the same for here in the second expression. This would multiply, this epsilon zz would have multiplied with that Poisson and with that expression, so I can say that contribution needs to be added here as well, and this contribution needs to be added here. And if I do that and I simplify the algebra, I get that plane stress condition. Okay, so then I essentially can derive that plane stress condition like that. Okay. The other thing that we just need to remember is also that this term and this term here, so these two terms are equal to 0. Okay, so they are both equal to 0, and the implication of that is essentially just that the shear components, these two shear components, are just 0, so they will fall away. Okay, the only one that's not 0 is this bottom one. That still remains. And so what we see is, so this bottom one, that still remains. And what we see is essentially that the first two expressions and this last expression is all that remains that we need to solve for. And that's why when you look at the plane stress conditions, we solve for little 3x3 system. So we solve for these stress component, this stress component, and these strain and this strain component. And that is what. But don't forget, after the fact, we can then compute the out-of-plane, non-plane response for epsilon zz. So this is just to give you a good overview of where the thing in the textbook comes from. And I would like to say for yourself, please go do the derivation, and it's a good practice maybe to practice a little bit again of SimPy if you want, just to simplify that expression and see for yourself that this if you've done this, exactly gets you to what you will see in the textbook for the plane stress condition. Okay.